Algebra 1 students, here are your 7.7 notes for the weekend. We're talking about exponential growth and decay. We've actually already begun this topic, but we haven't used some of the exact terminology and we've asked the questions in a little bit different ways. But the big idea here is that exponential growth or decay can be modeled by the function y equals a times b to the x power. A has to be positive. A is always positive for exponential growth or decay. And B is what we call the growth or decay factor. Now, how do you know if that is growth or decay? Well, B, as you can see in this gray chart to the right here, if B is a number larger than 1, then it's growth. In other words, you're multiplying by something more than 1, so that number is going to get larger and larger. But if B happens to be between 0 and 1, then you're talking about decay. Something gets smaller and smaller, sort of like the bacteria in your body. If after you take an antibiotic, that would be a decay situation where the amount gets smaller. Now you can see from the standard form of the equation, A is the initial amount. This is what you start with. The base is B. The exponent is up here. I don't think any of that's news, but let's go ahead and take a look at this and make sure we know how to identify the correct parts. Identify the initial amount A and the growth or decay factor B. I'm going to move through these pretty quickly. The initial amount on number 1 is 5. That's always the first term here, 5. And the B term, the decay or growth factor, is 3. Now, the question I probably should ask here is this growth or decay? And this is, of course, growth, because the B value is more than 1. Let's take a look at the next one here. Our A value is right there, it's 3. Our B value, even though it's smaller than it was on number 1, it's still more than 1, so what we have here is growth. Then things begin to change. If you look at number 3, the A value is real simple to pick out. It's just this coefficient out here, 6. But then the B value, what's being multiplied each time, is 1/2. And because that's less than 1, we're talking about decay. Now number 4 might be the trickiest of these. The key here is finding A, because there's no A term that we can see, but you'd have to think of it like this: y equals 1 times 0.8 to the x, and then you could see right away that A is 1 and B is 0.8. Now with the factor of 0.8, again, we know that's decay. Alright, a squirrel colony increases by 2% each year. The colony starts with 1,100 squirrels. How many will there be in 15 years? Now, we've done problems like this in the previous sections of this chapter, but we always gave you the equation to use. This time we're going to have to come up with it. So again, A is always representing the initial amount. And in this case, the initial amount would be the initial population of 1,100. And B, now this is where you have to think a little bit. The colony is increasing by 2%. This is where the growth and decay, here's your challenge. When it's growth, you have to add that number, 2%, to 1. In other words, to 100%. So it's 102% each year of what it was the year before. So we would call B 1.02. Again, we know it's growth because the colony increases, and therefore the B value has to be more than 1. You always add that percentage to 1, so 1.02. So what we're going to do then is say that y would equal 1,100 times 1.02 to the x power, and in this case we know that that exponent represents the number of years. So instead of writing an x, I'm going to write a 15. Now, this is not a problem we would want to do by hand by any means, so I'm going to use my calculator. You should use yours as well. We can punch it in just like this: 1,100, missed a 1 there, didn't I? 1,100 times 1.02, and I'm going to close the parentheses there and raise it to the 15th. and there's my solution. Now, one thing we know is that when we're talking about living organisms and something like a squirrel, we're not going to have 45 hundredths of a squirrel. So what we're going to do is basically just do a little estimation and say it's about 1,480 squirrels. On the next one, we're looking at a city that has a declining population. It starts at 73,000, but as you can see, it's losing 7% of their people each year. We want to know what the population would be in 8 years. So what we do for this is we're going to find those A and B values. Again, A represents the initial population, and that would be, in this case, 73,000. B is our multiplier. Now this time, you got to think just a little bit. It's declining by 7%. So instead of adding that 7% to 1, we're going to subtract 7% from the whole, from 1. So our equation will look something like this. Y equals 73,000 times 0.93 to the x, where x represents 1 year. Now in this case, we're trying to find out what the population would be at the end of 8 years. So we can go ahead and plug in that value right there. Again, it's back to the calculator, unless you have some pretty incredible mental math skills, stronger than mine. All right. And we'd have to go times 0.93 raised to the 8th. You'll notice on the first problem I used parentheses here on the calculator. The second one I just put the times button. Either of those things are totally acceptable. And in this case, y would equal about 40,849.47. So basically, again, we're talking about human population here, so we're not going to have 47 hundredths of a person, but something like 40,849 would be okay. And you could probably argue that something even more rounded than that, like perhaps 41,000, might even be more appropriate. But in any case, that town is quickly losing population. All right, next thing we're going to look at is compounding interest. This is something that we like it because it helps us make money, but it's also a fairly complex equation that sometimes people struggle to understand what's happening. So let's take a look at this. The formula, which I won't ask you to memorize, but I will ask you to know how to use it, is A equals P times 1 plus R over N raised to the NT power. Now it's all laid out for you here, but A represents the account balance, P is the principal or the initial investment, R is your interest rate, and that's in a decimal form. So if it's 7%, for instance, you wouldn't put 7, you would put 0.07. N is the number of times interest is compounded in 1 year. Now that's the one we have to think about a little bit, and it depends on your bank, so a little variation on that one. But basically what that means, if it's just compounded once a year, we'd call that annual interest, so your N value would be 1. If you had monthly, it would be 12. Quarterly would be 4. You could do all kinds of things. Daily, you could do month, or I think I said monthly already. You could do hourly. As you go into further math classes, you even find continuous, like constantly, infinite number of times compounding. So let's take a look at how the compounds affect money. All right, so here we go. This time we're finding the balance in the account with the given information. $1,100 is invested at 5%. So I'm going to start by writing this out. A is equal to the initial investment, the principal, is $1,100. Then we go 1 plus. Now the interest rate, it says is 5%, so we would write that as 0.05. Now note this says annually. When you see annually, that means N equals 1. So we're going to put a 1 here, and then it's raised to the 1 times 10, that's t is time in years, power. All right, let's go ahead and enter this. Now again, your calculator can handle this all at once. If you have your graphing calculator with you, you can just punch it in like I do here. 1 plus 0.05 divided by 1, although some of you may be thinking, Mr. Hale, you don't really have to divide by 1. That doesn't change anything. That is correct. And then we need 1 times 10, or again, you could just put 10 up there in the exponent. And in this case, we would have $1,791.78. Now let's take a look. The next problem actually is identical, save for one change. Daily tells us that n is 365. Now you might say, wait a minute, what about on a leap year? And you have a good point. It would have an incredibly small difference, but if you wanted to use 366, you could compare answers and you would see it would probably be to this exactly the same penny. All right, so now all that changes is instead of writing the n value of 1, we write an n value of 365. So let's see what happens. Interest is compounding a lot more times, 365 times rather than just simply once. All right, so I'm punching this in on my calculator, 1 plus 0.05 divided by 365, and we're going to raise that to the 365 times 10, so that's 3,650, and you can see the result there. So even though this is more money, it's a little under $22 difference on the investment that was left alone in an account for 10 years. I'll keep the 20 bucks. Don't get me wrong, but I just don't think it's a huge deal. And if you went to 366 instead of 365, I don't think you would even see any difference. As a matter of fact, since I have the video rolling, let's go ahead and change it. 3660, and instead of 365 we'll do 366, so this would be the equivalent of, it's leap year, it's 2016. Oh wait a minute, $1,813.53, exactly the same amount. Once those numbers get higher and higher, the n value gets higher. The difference between those steps becomes pretty small, and you can see the difference there. All right, let's look at one more. As a matter of fact, why don't you pause the video, give this one a shot. And welcome back, guys. You can see in my work here, 200 times 1 plus 0.08 over 4 raised to the 4 times 7, or 28 power, would give you $348. I hope that you've learned this. If you have questions, feel free to come in before school on Monday. Have a great weekend, and we'll talk to you later.